Good afternoon, everyone. This is Math 35, College Algebra at College of the Sequoias. Today we're looking at section 3.3. 3.3 is on the zeros of a polynomial. So let's just dive into lecture. So a zero of a polynomial, as we talked about in 3.2, a polynomial function is a value that when we plug it in, evaluates to zero, makes the function equal zero. Hence the name, zero of a polynomial. And recall we had f of x equals x minus k, q of k, or q of x plus some remainder. And so if k is a zero, then we have f of k equals k minus k, q of k plus r. And we're saying that a zero makes this equal zero. But k minus k itself equals zero. And so this whole thing is zero. And what that's telling us is r equals zero. So if k is a zero, then the remainder is zero. Okay. Polynomials can have as many zeros as the degree of the function. It's important to note, it's very, very important, this is crucial. They are not necessarily real. And what I mean by that is they can be complex. Take a second and write that stuff down. And okay. And so if k is a zero, what that means is that k comma 0 is a point on the curve which makes it an x-intercept. So knowing this can be a handy shortcut. We can plug in values, and if the function equals 0, the function evaluates to 0. That value is a 0, or it is an x-intercept. Let's do an easy one to work with. So this is a quadratic function. We have a equals 1, b equals -5, c equals 6. We need it to multiply to a times c, which is 6, and add to -5. For it to multiply to a negative number, or to a positive number, they both have to have the same sign. For it to add to a positive number or a negative number, they have to both be negative. -2 and -3 work. Since a equals 1, I can shortcut this to x minus 2 and x minus 3. And remember, if we're saying these are zeros, then f of x equals 0. We're trying to find zeros here. And we get x equals 2 or x equals 3 are zeros. Or alternatively, which I don't necessarily think is easier in this case, evaluate these at those values. F of 2 equals 2 squared minus 5 times 2 plus 6. This is 4 minus 10 plus 6, and that does equal 0. Why don't you pause this for a second and you show that f of 3 equals 0. Okay, I'll assume you did it. I get 9 minus 15 plus 6. That does equal 0. The zeros have another name. Zeros of f of x are called the roots. Or solutions to f of x. Sorry, you might hear my dog barking in the background. We just had Instacart making a delivery. Trying to stay safe in these trying times. Let's check this concept out on a bigger problem where it's a little bit harder. Let's look at f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. I'm off the screen. And let's do some test values for k. Let's try k equals -1, 0, and 1. I'll start off with k equals 1. So we'll make our synthetic division box. The easiest way to go about doing this. Those are our coefficients. And so we start off, we bring the 8 down. 1 times 8 is 8. Negative 26 plus 8 is negative 18. 1 times negative 18 is negative 18. We add those up. This is 15, carry the 1, 45. 1's an easy number to do because then you just move the number up. 11 minus 45 is negative 34. And this is negative 30. That's my R. So this tells me k equals 1 is not a root, which means x minus 1 is not a factor of f of x. So let's give it another try. K equals 0 is easy to try. K equals 0 is a really easy one to try. That's even easier than 1. Because it doesn't matter what we bring down. 0 times 8 is 0. R equals 4. And we knew that already without actually plugging in 0. We could have just done f of 0, and that clears out anything with a variable, and we get the remainder is 4. It's the only thing that wasn't a variable. So again, not a 0. Okay. Why don't you guys try k equals negative 1, and then we'll do it together. All right. I'll assume you did it. Makes that positive 34. That adds up to 7. Negative 7 is 4. Negative 4 is 0. K equals 1 is a root, which means x minus k, which is x plus 1, is a factor of f of x. And it tells us what's left over. We've got x plus 1, and these are the coefficients of what polynomial 1 degree lower. 8x cubed minus 34x squared plus 7x plus 4. And if we wanted to keep going, we'd start working with this one rather than the bigger one because there's less numbers. Okay, I'll assume you pause this and work with it. So randomly testing different k's suck. But let's get some more practice in before we go on to the next thing. I'm going to tell you the first value of k that works. x equals 5 is a zero of f of x. Factor f of x completely. That's our instructions. So what we're going to do, we'll start off, we'll use synthetic division with k equals 5. And this will help us find q of x, our remainder, our quotient. And then we'll have f of x equals x minus 5 times q of x. And then we'll factor q of x. So go ahead and give that a try. I gotta get it, okay. Pause it while you're doing so. All right, I'm gonna continue. I'm assuming you pause and work through it. We bring down our 6. 5 times 6 is 30. We add that up, we get negative 7. 5 times negative 7 is negative 35. That gives us negative 3. 5 times negative 3 is negative 15, and that gets us 0, which we knew because we already said it was a 0. But this tells us q of x is 6x squared minus 7x minus 3. Now, you can keep trying synthetic division and coming up with numbers, but we have a quadratic function now. We can do factoring. I'm going to give it a try. If factoring doesn't work for me right away, I'll go to the quadratic formula. A times c is negative 18. B is negative 7. I have two numbers that have to add to a negative number, which means the bigger number is negative. And they got to multiply to 18, negative 18. Negative 9 and 2 work. A does not equal 1, so I can't just jump to putting x minus 9 and x plus 2 in parentheses. I have to split this up. And factor by grouping. I can pull out a 3x, and that leaves 2x minus 3. I need another 2x minus 3, which means I got a plus 1. We finish factoring q of x. 3x plus 1 times 2x minus 3. The answer to our problem, though, was to factor f of x. So our solution, we still have that x minus 5, and then we have this 3x plus 1 and 2x minus 3. All right, I'll assume you pause and are ready to go on. Let's work with that one a little bit more. What are the zeros of f of x? Well, the zeros of f of x are, we know it has to equal 0 when we're done. And that means x minus 5 times 3x plus 1 times 2x minus 3 have to equal 0. And we can set each one equal to 0 and solve. And we get x equals 5, negative 1/3, and positive 3/2. So I don't know if you've noticed, but if looking at that 6x squared that we had, the last function for q of x, guessing k's there would have sucked. I don't think I would have ever guessed -1/3 or 3/2. Guessing zeros is a pain in the ass. It is. It's a big pain in the ass. Thankfully, there's been some smart people in history and mathematics that have come up with some cool shortcuts. The first one is called the Rational Zeroes Theorem. Rational has ratio in it, which means fractions. We can have fractional answers like we did. -1/3 and 3/2 are fractions. And this is how the rule goes. If P over Q, and I haven't told you what P and Q are yet, if P over Q is a simplified rational fraction, we want it as simplified as possible. We don't want like 9/6, we want 3/2. Is a simplified rational number, and f of P over Q equals 0. And another requirement, f of x has integer coefficients. We don't want any fractional coefficients or decimal coefficients. We want to have integer coefficients. There's a lot of requirements there. So P over Q is a simplified rational number. When plugged in, it evaluates to 0. And f of x has to have integers as coefficients. It tells us two things. A, Q is a factor of the leading coefficient. And B, P is a factor of the constant. Now I'll let you soak that in, and then we'll do some more with it. Okay. I'll assume you paused and wrote that down. Let me show you what all that means. That's a lot of math lingo and jargon, right? So let's just use the function we just did. The function we just had was we had 6x cubed minus 37x squared plus 32x plus 15. We already know the zeros, 5, -1/3, and 3/2. Those were our zeros. This 6 has the factors of Q. 15 has factors of 5. Or P, sorry. So we're going to factor 6 in as many ways as possible and write down all the combinations. So factors of Q, well, I can have 1 and 6 or 2 and 3. I'm going to put them in numerical order, and I'm going to list plus or minus on each one, because I can always do 2 negatives to end up with a positive. P has a fixed number of results also. We've got 1 and 15 or 3 and 5. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And so now let's look at our options for P over Q. And sometimes it helps to stay with one denominator and go through it. So let's look at Q equals 1. And it can be the plus or minus 1 because I'm going to just list all the plus or minus answers. I'm going to put P, all my factors of P, over 1. So I can have 1 over 1 and the plus or minus version. I can have 3 over 1. I can have 5 over 1. Or I could have 15 over 1. So all the options for all the factors of P are automatically possible answers. Then we'll look at Q equals 2. And we'll put P over all of these. 1 over 2 is 1/2. 3 over 2 is 3/2. 5 over 2 is 5/2. 15 over 2 is 15/2. You guys see what we're doing here? I'll do one more with you, and then I want you to do the number 6 without me. So we'll have P1 over 3. We can have 3 over 3. I can have 5 over 3. And I can have 15 over 3. Now, I want simplified options. 3 over 3 simplifies to 1. And I already have 1 listed. I'm going to cross that off. 15 over 3 gives me 5. And I already have that. I'm going to cross that one off. I don't need those options because I already have them listed. Why don't you guys try the same for Q equals 6? And make sure to simplify when you're done. Go ahead and pause it while you're working if you would. All right. Q equals plus or minus 6. I get 1 over 6. I get 3 over 6. I get 5 over 6. And I get 15 over 6. 3 over 6 simplifies to 1/2. And I already have that listed, so I'm going to cross it off. $15 over 6 simplifies to, I can divide each of these by 3 and I get 5 over 2. And I have a 5 over 2. I'm going to cross this one off as well. So those are my options. There's a lot, isn't there? I mean, we got to do plus or minus versions of each of them. But notice the zeros we said, x equals 5. X equals -1/3, and x equals 3/2 show up on those lists. It's important to note, this is vitally important, crucial information. These are only possible rational roots. None are guaranteed. We may not have any rational roots. We might have all complex answers. It's unlikely we'll end up with irrational roots, but it's possible. I think. No, not really. I'm having trouble thinking of an irrational root that might, well, it might. There's quadratic formula does give solutions that are irrational. No, the quadratic formula still always reveals fractional answers. Well, they sometimes have square roots in them. So yeah, there are roots that are irrational. There are complex roots. So if there are rational roots, they're on this list. Okay. So I hope you pause there. You're ready to go on. So what we're going to do now, what I want you to do, I want you to pause and do this. We're going to have f of x equals 8x to the fourth minus 26x cubed minus 27x squared plus 11x plus 4. I don't want you to find the roots. I just want you to find all possible rational roots. So pause it and try giving it. So we're looking for P, all the different combinations of P over Q. I hope you guys are enjoying the video lectures. I'm a little bit ahead on the other classes. I'm focusing on doing a ton of lectures for you guys this week. Okay. All right, I'll assume you did it. Q comes from 8. So our Q options, we've got plus or minus 1 and plus or minus 8. But 2 and 4 are also options. And then P, we've got 1, 2, and 4. Those are the only factors of 4. So P over Q, 1 over 1, which is 1. I feel silly saying 1 over. I think I even left 1 over 1 on another page. No, I didn't. Good. That's a scrub move. Plus or minus 1. So all the P's are on the list. Plus or minus 2, plus or minus 4. Then I can put 1 over 2. I can put 2 over 2. 2 over 2 is already 1 and it's already on the list. So 2 over 2, done. 4 over 2 is also on the list. That's 2. So we don't need either one of those. And now I'll do my 4. Now I'm looking at Q is 4 on bottom. I've got plus or minus 1/4. Plus or minus 2/4 is 1/2, done. And 4/4 is 1. That one's done. And then we'll do a denominator of 8. 1/8 works. 2/8 simplifies to 1/4. And 4/8 simplifies to 1/2. These are my P over Q that are simplified. These are the repeats. So that there's still 12 numbers to check there. That's still a lot of numbers to check. We're not out of cool theorems though. Let me pause and let you jot that down a little bit. All right. Next theorem, Descartes. And this one's trippy. This one's really trippy. What you're doing here is looking for sign changes in f of x. And I'll show you what I mean. What we're going to do is we examine f of x. However many times it changes signs. Is the number of possible positive real roots. So positive and real. Maybe not rational though. We might have irrational numbers that are positive, but they'll still be real. So let's look at the f of x we just used. Eight is positive, and I go to 26. There's a sign change, plus to minus. Negative 26 to negative 27 is minus to minus. That's not a sign change. Negative 27 to 11 is a negative that changes to a plus. That's a sign change. And 11 to 4 is positive to positive. That's not a sign change. I've got 1, 2 check marks, 2 possible positive roots. And we found them. They were 5 and 3/2. Wait, was that this problem? Nope, that's a different problem. Ignore that. 2 possible rational roots. Positive rational roots. And how that helps us, if we use that with the Rational Zeroes Theorem, or the Rational Zeroes. If we find 2 positive roots, we can cross off all the other positive ones. Okay. I'm going to remove the old page now. Pause it if you need to, because we've got a second part to Descartes' theorem. So part B, examine f of negative x for sign changes. This gives us all the possible negative real roots. So we had f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. When I stick in negative x, I'm replacing the x inside parentheses like this. Now, there's a shortcut to doing this. If the exponent is even, sign stays the same. And if it's odd, sign changes. So f of negative x to the fourth, it stays the same sign, 8x to the fourth. Negative 26 times negative x cubed, the exponent's odd, it's going to change signs to be positive 26x cubed. Negative x squared, it's even, we're going to keep the same sign that we had before. Negative x is to the first power, it's going to make it so we change signs. And the 4 doesn't change signs. Okay, now I go through and look for sign changes. Positive of positive, no. Positive to negative, yes. Negative to negative, no. Negative to positive, yes. So there's two possible negative real roots. Again, they don't have to be rational. And you know what's even worse? The roots don't have to be distinct. Distinct or unique. They can repeat. What that means is if we find that 1 is a root, 1 might show up again as another root. So we may have to check that number again. Ready for example? We'll make it a short one for a second. Let's just look at f of x equals x squared plus 2x plus 1. So f of x has no sign changes. So no positive real roots. F of negative x becomes x squared minus 2x plus 1. There's a sign change, there's a sign change. F of negative x has two sign changes. So we could have two negative real roots possible. We actually know what that factors to. You could factor it real quick. That's x plus 1 and x plus 1. If we set that equal to 0, we find the two roots are x equals negative 1 and negative 1. I hear spray. My wife must be disinfecting the groceries. Okay, so when we have roots that are repeated, they get a special name. We call it multiplicity. So here, the roots are x equals -1 multiplicity of 2. It tells you how many times the roots are repeated. So that's another tool in our toolbox. Descartes Theorem, Rational Zeroes Theorem. We got another one, and this one's kind of incredible. It's called the Intermediate Value Theorem. This is one of the most important theorems that you'll work with. Intermediate Value Theorem. And the way this one works is we have a requirement. F of x has only real coefficients. They can be fractions. The Descartes theorem doesn't work with fractions, but intermediate value theorem does. F of x has only real coefficients. That's the requirement. Then for real numbers a and b, we used a and b because they can take any values. If f of a and f of b have different signs, there is a root or zero between them. I'm going to show you pictorially what that means. Graphically, it's kind of helps clear it up. Pause this and finish writing this down. Okay. So what that means is this. I could have some setup like this. This is A and this is B. I could have f of A and it's some point up here. And I have f of B and it's some point down here. So here f of A is greater than 0 because this is the x-axis. And this is y. Y is a positive above it. And B is negative below it. And it doesn't matter how the line wiggles. It could do something like this. But it eventually has to cross somewhere. And that's the root. Now, it may not be rational. It could be irrational. But it's going to cross somewhere. And it could be the other way. We could have f of A down here. F of A is negative. F of B is positive. And wiggle, 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 yeah. Root. Now, does that kind of make sense? It crosses somewhere. The chicken doesn't start on one side of the road and get to the other side of the road without crossing the road. It's as simple as that, you know? However, if they have the same sign, it tells you nothing. That's y, x. Let's say this is A and this is B. So this is f of A, it's greater than 0, f of B greater than 0. The chicken could stay on the same side of the road the whole time. Oh, Frogger. Frogger's even better. If you've ever played Frogger, you're a frog trying to cross a busy street. It's an old game. And you die when your frog gets run over. So the frog may never, your goal is to get across the street. So the frog may never cross the street, or the frog may go back and forth, cross the street a bunch of crazy times and get there. This has no roots between them. This has a lot of roots. So when they're the same sign, it doesn't tell you anything. All right, so let's put these three ideas all together and let's go look at that last function we did. And we've already written down the roots. We had f of x equals 8x to the fourth minus 26x cubed minus 27x squared plus 11x plus 4. And we said P over Q, we found them out. We had negative 1/8, negative 1/4, negative 1/2, negative 1, 2, and 4. You may find it helpful to write them in, and these are plus or minus. Oh, these are all the less than 0 ones. So we got, these are plus or minus. Let's write them in order. The smallest one would be negative 1/2. Let's note negative 4, negative 2, negative 1, negative 1/2, negative 1/4, negative 1/8. Those are my negative numbers. And I've got positive 1/8, positive 1/4, 1/2, 1, 2, and 4. And we did Descartes Theorem. That's the sign changing one. There was 2 positive and 2 negative possible real roots. Okay. So a good idea is if Descartes says one of them has more options than the other, like say 6 positive and only 2 negative, do the one that has the bigger number, because you're more than likely going to find a root faster, and you can shrink that polynomial down and make it easier to work with. So if Descartes shows one has more options than the other, like 6 positive, 2 negative, go with the bigger option. Because you're more likely, probabilistically, because probability says you're more likely going to find the root faster. You should find the root faster. So that's pro tip number 1. Number 2, don't try them in sequential order. Okay. Bouncing around allows you to use the intermediate value theorem. And this theorem comes up so often, this is a well-known abbreviation, IVT. Ooh, my page is totally starting to rotate. Okay. So let's start looking at options. I'm going to leave those numbers showing up there. And I want my f of x showing too. Let's say we start with -2. Let's try k equals -2. Let's see if it's a root. We're going to focus on the negative ones first. If we find 2 of them, we're done with the negatives. -2 times 8 is -16. We add that up, it's -42. -2 times -42 is +84. And we add those up and we get 57. We multiply that, we get -114. This adds up to -103. This is +206, which gives us 210. So f of -2 is greater than 0. If I find another negative root that's negative, then maybe the one between it works. So rather than trying -1, I'll jump to -1/2. Let's try -1/2. Eight times -1/2 is -4, and that adds up to -30. -30 times -1/2 is 15, and that adds up to -12. -1/2 times -12 is 6. Those add up to 17. So this is -17/2. 4 is 8/2. This adds up to -9/2, which is less than 0. So f of -1/2 is less than 0. F of -2 is greater than 0. F of -1 may work. If there's a negative root in between -2 and -1/2, it's got to be -1. So if there's a rational root between them, it must be -1. That's because we've got -2 and we've got -1/2, and we're looking for P over Q in between them. And the only one left in there is -1 according to our list up there. We've got them in order. -1 is the only one that shows up. So let's check it. In fact, you guys check it. I'll leave that up there for a second while you finish writing it. Now, if it doesn't work, there's still a 0 there because it has to cross the line. It just means it's not rational. Okay? Like negative square root of 2 is irrational, but it's between negative 2 and negative 1/2. So it could have an irrational root in there. Okay, I'm going to assume you pause it and are working it out. Does f of negative 1 work? Yes, I think we did that one already. I think we said start with negative 1 and show that it works. So k equals negative 1 is a root. K plus 1 is a factor. And now f of x is down to x plus 1 times 8x squared minus, not 8x squared, 8x cubed minus 34x squared plus 7x plus 4. Okay, and we could keep going through it and keep working. I want to cover some more theorems with you. And I actually told you this next one earlier, but I didn't tell you what it was called. In fact, it's so important, they call it the Fundamental Theorem. The Fundamental Theorem of Algebra. And it's a little confusing because it's a little misleading. Every polynomial function of degree 1 or higher has at least one complex 0. So we've got z equals a plus bi. Now it makes it sound like there's a complex solution. But if b equals 0, z equals a and is real. So there's complex solutions or real solutions. And it has at most the degree of the polynomial. It should have the degree of the polynomial. A bunch of them may be complex and they may be really, really hard to figure out. You don't know how to factor them and get them, but they should exist. Ready for more? Let's give an example of that. We've got f of x equals x squared plus 1. if we want to find the zeros of it, we set it equal to 0. This doesn't factor. But if we subtract 1 to the other side and take the square root of both sides, we see that x equals plus or minus I. So x equals I or x equals negative I. And I know I just said that. They actually give a name to the other one. It's called the number of zeros theorem. A polynomial of degree n has at most n distinct roots. The reason why they say at most is if there's multiplicity, there's still n roots, but they aren't all distinct. Let you process that for a second. Okay. Here's an example. I will show you the shortcut in the future to how to find the roots to this. This is x plus 1 times x plus 1 times x plus 1, which is x plus 1 cubed. If we set that equal to 0, x equals negative 1 is the only root, but it has multiplicity of 3. Okay, so here's some other things they'll give you. These are actually good mental challenges. I'm going to walk you through how to do a couple of them like this. They'll tell you, here's an example. Find a third degree polynomial that satisfies the following conditions. A, the zeros are -3, -2, and 5. B, f of -1 equals 6. So what does A tell us? It tells us x equals -3 is an answer, x equals -2 is an answer, x equals 5 is an answer. And if we move them to the other side, we have x plus 3 equals 0, x plus 2 equals 0, and x minus 5 equals 0. This is like factoring, finding the solutions, and working backwards. It very much is. And now I can take these and multiply them all together, and I still have 0. Nothing's changed. That still equals 0. Now, that might be f of x. Is it f of x? Well, part B tells us f of -1 equals 6. So let's try this. F of -1 is -1 plus 3, -1 plus 2, -1 minus 5. Is -2, -1, -6, and that multiplies to -12. Not 6. So something's missing. The problem is that we're saying that this tells us if we multiply it out, the leading coefficient is x cubed. What if the coefficient, let me pause and let you write that before I turn the page. Okay. What if the leading coefficient isn't 1? Let's put an A in front. I don't know what it is, but I'm going to call it A. Now, if I plug in -1, I know this has to equal 6. We just worked this all out. This was -12. So I've got f of -1 equals -12a, and that has to equal 6. I can solve for a here by dividing by -12, and I get a equals -1/2. And so f of x is -1/2 times x plus 3 times x plus 2 times x minus 5. You should write this, multiply that out, okay? We don't leave them like that. In fact, I'm going to give that to you as a challenge. When I multiply that out, I get -1/2 x cubed plus 19 halves x plus 15. See if you get that. We'll do one more example like that. See if you can figure it out. 4 is a 0 with multiplicity of 2. F of 2 equals 8. Pause it and see what you come up with. Well, 0 it being a 0 means x equals 4 is an answer, which means x minus 4 equals 0 is an answer. And it's called multiplicity of 2, so there's 2 of them. So we're going to have f of x equals a times x minus 4 times x minus 4. And now we'll evaluate f of 2. That has to equal 8. Two minus 4 and 2 minus 4 are -2. And this tells me f of 2 equals 4a, which has to equal 8. We divide by 4 and we get 2 for a. And that's 2 times x squared minus 8x plus 16. And if you multiply it out, 2x squared minus 16x plus 32. And that's the answer. So that's kind of it for the zeros of the polynomials. What we're doing next is we're going to use those to graph these crazy functions. Okay, so 3.4 is on graphing and doing even these crazy graphs with 4th degree and 5th degree. We're going to show you how to do it. It's kind of neat. Okay, that'll wrap up 3.3. And I'll be making 3.4 likely tomorrow morning. And on Tuesday morning, 3.2 or 3.4, hopefully 3.5 and 3.6, or the next few. I'm going to try to get through chapter 4 this week. I'm focusing entirely on this class this week. We'll have a lot of videos for you well before spring break starts. We're going to make sure you all pass this class. Peace.